Hey, welcome back to Accidental Science. So let's say that you want to make a measurement of the mains voltage with the oscilloscope, but you don't want to fry your precious oscilloscope. For this job you should use a differential probe, but you don't have one, and differential probes are pretty expensive. And you don't want to spend that much money because this is one-time measurement in your life. So what to do? Okay, I will show you a possible, simple, cheap DIY solution. Stick with me. Why it is risky to measure the mains voltage with the oscilloscope directly hooked the oscilloscope to the mains? Why? Because if you accidentally connect the ground of the oscilloscope that is connected to the protective earth through the cable through the cord of the oscilloscope, and you connect this to the lead wire of your mains, you will fry your oscilloscope. Either you will burn the probe or you will melt the traces inside of the PCB inside of the oscilloscope. So let's see what's the problem. This is a system TT, but even with the TN system, the problem is similar. So we have here the line that comes from the power station and arrive at a local transformer. And here we have the local transformer that is usually connected star or Y, where the center is grounded through a spike into the ground, and the three phases are provided to the user, maybe two phases of the three or all the three phases, and that's dependent by the contract you have with the utility company. And for simplicity, here we look only at a single phase, so neutral and one of the three phases. It's not important. And here we have the RCD that is mandatory with the TT, and then the wires go. This is the neutral, go to the sockets, and this is the lathe that go to the go to the sockets. And here we have our oscilloscope that is connected to one of the sockets, and the two wires that provides the power goes to a transformer, so there's no electrical galvanic connection between this point and the internal power supply of the oscilloscope, but the ground is connected through the socket to the main ground, the spike ground here. So the ground is why the neutral is at the same level of the ground. When it is in your house in a TT system, the neutral is never at the very same voltage as the ground. It could have a little difference, but it is not that important for this case, this specific case, because here we use the probe, and suppose you use the shield and connect the shield to the live. So as you can see here, we have a beautiful short. So to make it clearer, I traced the path in red, so the current will flow through this line across the shield, along the cable of the probe, across the internal traces of the oscilloscope, and then back to through the cord of the oscilloscope, the ground into the cord of the oscilloscope, and then along the wire, the ground wire of the sockets in your home, down to the spike, through the ground to the other spike, and back to the transformer, including the loop. Of course, here there is a resistance, but this resistance is pretty low, and so we have a high current that will flow across the circuit. One might could think, well, I could hook directly the probes to the mains. Even if you connect this to the neutral, still the probe likely will not be rated for that much voltage. Because, yeah, if you are on under 10 volt, it's okay. But when you are on 20, 30 volt, which means 325 volt peak, then your probe is likely not capable to handle that much voltage, neither the input of your oscilloscope. Perfect if you like a dangerous life. So we have to address two problems: voltage and the return through the ground, the protective earth. To solve these problems, basically we can use 4 resistors connected this way. Here we have the probes that goes to the point of measurement at mains level. That can be 110 volt, 220 volt, or even 400 volt AC RMS. And here we have the output that goes to the oscilloscope. And because this point is tied to ground, and this point is at the same potential of the ring of the BNC input of the oscilloscope, that in turn is connected to ground at its chassis, this point is guaranteed, these points are guaranteed to never ever go to a dangerous voltage for the oscilloscope. And at the same time, we guarantee that the input probes never ever will have the chance to connect directly the ground to one of the point of measurement, as we would have if we used the input probe directly, the input probe of the oscilloscope. Also, we can notice that we have here a differential voltage. So we have to solve this to measure to have a meaningful measurement for the oscilloscope. And to solve this, we just can use 2 probes. One is connected here, and the other is connected here, and we use both A and B channels of the oscilloscope with the math function difference to get the actual measurement of the input. And of course, the ring here is connected here, and this ring is connected here to this point that is tied to ground. First off, we have to prevent the risk that the RCD could trip because of the current that flow through this branch and this branch toward ground. This is pretty easy to solve because if we have here, if we put here a resistance of let's say 1 megohm, we have a current that is just 320 microamps approximately. And to have a ratio of 100 to 1, we have to put here let's say 99 kilo ohm, and here, sorry, 990 kilo ohm, and here a resistor of 10 k. But we can't use just one resistor, 990k resistor, because the voltage that will drop here, that will be across this resistor, will be too high. If we give a look at this data sheet from Vishay, for high stability, high precision axial metal film resistors, we can see here, let's zoom a little bit, we can see that for resistors of 1/4 of watt in power, we can reach up to 500 volts. That is good, but this is not always the case, because if we give a look at this other data sheet, this voltage here, you can see that the 1/4 watt resistor can withstand 200 volt, this model, or 250 volt, this other model, which is the typical value that we can find on this kind of resistors. Even this one that are at low tolerance, 1% tolerance. So to solve this problem, we have to split this and this resistors into 4, like this. So we have 4 resistors in series of 270k ohm each, at 1% of, if not better. So the series equates to a total of 1080 kilo ohm. Here, however, we have to change this resistor to maintain the ratio. So we have to change this resistor to 10.8k. But what if this resistor got broken and it becomes interrupted, and like this, and the resistance here becomes infinite? We no longer would have a current that flows here, so here the voltage would be the same here, frying your oscilloscope. And that is clearly something you don't want, don't you? So instead of one resistor, we put 2 resistors in parallel, each one of 22 kilo ohm. So that's the resulting resistance is 11k, because between 180k and 11k the ratio would not be correct. We added another resistor here of 560k in parallel, which give us a total in resistance here of 10.788 k ohm, which is pretty much the required value to get a correct ratio 100 to 1. And we solved all the problems, because if one of these resistors got broken, then we have another resistor here that limits the voltage twice the voltage that would have been, which is not much, because if we consider that we have here, suppose 400 volts, and this point is let's say connected the same potential of ground that we have. So we have from here to ground 400 volts. The resulting voltage here is 8 volt, which is not much, and the oscilloscope will withstand without any problem. So this is the final circuit. We have here 4 resistors in series of 270k each. Here the 2 resistors in parallel, 22 kilo ohm, each, and here this resistor in parallel, 560k. All the resistors must be 1/4 watt, 1%. One important point is here the probes of the oscilloscope must be set to have an attenuation of 10 times. So the voltage that you read here at the oscilloscope is 1,000 times smaller than the voltage that is applied here at this at input, because here we have an attenuation of 100 to 1, and here another attenuation time to 1, so the product is 1000. Oh, don't worry, I don't use this to clean my teeth. So let's see a practical example. Here inside these two tubes we have the resistors in series, and here we have the resistors that goes to ground, which is this wire. And for the sake of the demonstration, I've omitted to make the parallel and just put a 10K resistor here. And here we have the two probes that are set to an attenuation of 10 times. And here the wires goes to this cable that goes to this plug. So let's put the plug inside the socket and try this circuit. Now this is not electroboom, so don't expect explosions. Yeah, here we go. We have the voltage at the oscilloscope, and we can see the sinusoid from the main, so that is a little bit distorted. And here we have the two channels that are set at the same amplitude, and the function that is used here is the addition with one inverted channel. Sorry, that was a mistake. Okay, with one inverted channel, so the net result is a subtraction. For the digital oscilloscope, we have here the yellow tracer, that is channel 1, the pink trace is channel 2, and the pink trace is almost invisible because the wire is the neutral, which is close to ground, so we have a very little voltage here. And the white trace is the difference between the two traces, which is the actual value that we are reading from the mains. And of course we see the two probes are set to be 1000 attenuation. So we have 200 volts per division here. The oscilloscope calculates the correct division, the correct voltage per division. So we can read here directly 200 volts per division, and this is the same for the calculated value here, the white trace. Where's the cursors? The cursors are here. So let's adjust the cursor here. Okay, so we have here a voltage of 572 volts, about, more or less, which is not exactly correct, because 572 volts divided by 2 gives 286 volts, divided by 1.41 and gives 202 volts RMS. That is not the real voltage we have here. If I measure the resistors, I see I have 1.1 kilo mega ohm instead of the 1.080 kilo ohm, which is a pretty remarkable difference, because I've used regular resistors with a Y larger tolerance. And that explains the difference in voltage we have read at the oscilloscope. The side of the tubing, and okay, we can see there is a series of resistors that are connected together to form the attenuator. One last word of caution: if you remove the connection here to the ground, you still have a connection through the probes and through the cord of the oscilloscope to ground. But if this cord is defective, or the ground that the protective earth that would carry the ground here to the cord of the oscilloscope is broken, then you would end up to be hooked to the mains in some ways. So it would be still hazardous, let's say. And in general, pay some cautions when you work with mains. Well, I hope you enjoyed this video. If so, please like, subscribe and share the video with your friends, because it is a way for me to know that I have done a good job. So for now it's all. Oh, wait! The next time we will see another kind of differential probe. This time a probe, an active probe made out of simple operation amplifier, and this will free up one of the two channels of the oscilloscope, so we can read directly the mains with one channel of the oscilloscope. Thanks for watching, see you next time, bye.